Good afternoon, everybody. Everybody done with their lunch coma? Everybody equalized now? Welcome. This is the second of 4 Cisco sessions today. Glad you were able to join us. I'm going to be introducing our presenters in just a second. I did this in the first session, and Ben, you're automatically now disqualified because you won. In the keynote yesterday, Jonathan asked how many people were here at a summit for the first time, and I was impressed by the number of hands that went up. I'm going to go the other direction.
Oh, shit.
I want to know who's been to, and Shannon, I think you're automatically disqualified too. Who's been to more than 5 summits? Okay. More than 10. You also disqualified. Which was your first? Paris? Okay, that's 11, because this is my 12th. No, that's 10. That's 10. That's an even 10. You, sir, are the winner of a lovely Cisco flashlight. Oh my God, I hope it makes it. Okay. Again, thank you all for coming. I'm going to quickly introduce our 2 presenters. I'll let them tell you a little bit more about themselves. Gokul and Mohammed from Equinix. We're going to be talking about some edge services on OpenStack, and take it away.
Perfect. Good afternoon, everyone. Welcome to the talk. Today, I'll be talking on network edge platform that we built on top of Cisco CVIM platform. So Gokul and myself will be co-presenting this slide deck. I will walk you over the challenges that we have when we start evaluating OpenStack and other virtualized platform with startups, and then how we end up being with CVIM, and what are the various deficiencies we see currently in OpenStack, which is mostly a product, but which is not a product, but bits and pieces. Things are there, but major things that we were looking for, which is network heavy, are missing. So I'll walk you through a journey. I will talk about how we build this software stack and hardware stack, and then how we enable various use cases for hybrid multi-cloud. I'll spend like couple of minutes on what is Equinix. Equinix is a data center company. They have close to 54 metros across the world, 220 data center, and we keep growing. We have 3 regions, EMEA, and Asia Pac. The objective of Equinix is simple. It's an interconnection platform for world-leading business. You bring in your data center to Equinix, and we can connect you in any place in the world. That's how the interconnection fabric is. What is the purpose of Equinix is we want to protect, we want to connect and power the digital economy through our data centers. We offer services to the customers, and there are multiple products. I'll just talk about 2 products because these are the 2 products enable us, our customers, to go to the cloud or bring their branch office traffic from the internet. So these 2 products are, the first product we call it Equinix Cloud Exchange. Customer comes to Equinix, build their cage and build their data center in the cage. In the middle, you are seeing Equinix Cloud Exchange product. All these big service providers, Amazon, Google, Microsoft, Oracle, we have close to 300 CSP endpoints directly connecting with 10 gig and 100 gig to our platform. So we can offer a direct connect of 1 gig, 10 gig speeds from your private cloud to your data center. So that's one of the drive of our Equinix Cloud Exchange Fabric. Second thing Cloud Exchange Fabric is doing is you have to be on Equinix premise. So you have to build the cage. I'm going to give you a physical cable to my fabric, and then I can orchestrate these virtual circuits. So the market we are tapped with this ECX is anyone who's an Equinix premise can be connected to any cloud destination. What if you are not on Equinix premise? You still own the private clouds on Amazon, Google, and Microsoft, and you want to connect them together without being physically present at Equinix location. So that's the problem we try to solve with this virtual point of presence. So Fabric ECX giving you cloud access. The second product, we're calling it Equinix Connect. This Equinix Connect enable you to bring your traffic from your branch offices to Equinix data center and then go to the cloud. So these 2 products, I'll talk more in next slides. So how Equinix footprint look like? Equinix has 54 metros, 220 data centers. All these locations popped up here, red and black means we have our fabric available, and this fabric is all interconnected across the world. So if we provide a platform which gives user a virtual point of presence to connect their cloud, then we are tapping into a market where customer doesn't need to be on Equinix data center, but they can still traverse traffic through Equinix and can get high-speed pipes, 1 gig, 10 gig, 40 gig, that they cannot get through the internet. So now we had a network edge service as a product vision. The requirement of that product was we need to build hybrid multi-cloud product because data center cannot go completely on the cloud. It has to be hybrid. Customer wants to keep control of their data, but they still consume the goodness of the cloud. So product has to be hybrid. Multi-cloud means you can buy wholesale VM from Amazon, you can buy wholesale data center database from Google, wholesale storage from Amazon, right? But then you need to connect all of these together. How you do it? You cannot do it through internet. You need sub-millisecond latency so you can connect a VM with the storage and install a database on top of it. So that's one of the use cases we're trying to solve. So now, present mode of operation, you have internet, you have Microsoft, Amazon, Google. I just put 3 big clouds there. So if customer has these private clouds on these 3 CSPs, how currently they do the connectivity? They create internet connection between these 2 PVCs that they have, and they build IPsec tunnel. So you're going over the internet, you get limited bandwidth, then there's a latency issues there. How you solve this problem with Equinix? So we have this E6 fabric I talked about, and these clouds are connected with 10 and 100 gig of bandwidth, direct connect to Equinix. They have private clouds, customers have their private cloud hosted on the CSPs. If we build a product, infrastructure as a service product, customer can come to Equinix portal and say, I want to connect my cloud on Microsoft, Amazon, on Google, give me 1 gig of bandwidth, and boom. What will happen? What will happen is we will create a VNF, which will be a routing VNF. We will create a direct connect from their private cloud to Equinix Fabric. We will extend it, terminate them in a routing instance, so customer has multi-tenancy. Extend the VNF towards the clouds, stitch them through EVPN, and do the BGP. With that, the customer does not need to be on Equinix premise. If you see here, the VNF is a virtual point of presence. Now, how the traffic will flow? Traffic will flow through a private network, not through internet. The goodness here is it's all private. It can get up to 10 gig or 40 gig of bandwidth that you cannot get from the internet. And goodness is you don't have to be an Equinix. It's pay-as-you-go model, right? You just come up, you swipe your credit card, and you get connected. So that's the vision that when we started this product, that's the vision. Bring in customers, give them good private network. Let them not worry about the security. We'll consume the security, and then easy to connect their private clouds. So platform Equinix, the vision was it has to be a vendor-neutral product. We want to host routing VNFs from Cisco, from Juniper, from Arista, whatever you like will be there. So vendor-neutral routing, vendor-neutral firewalls, Palo Alto, Fortinet, and then vendor-neutral SD-WAN solutions. So anything we will host here will be vendor-neutral. So this is infrastructure as a service platform. We'll host vendor-neutral VNFs. Subscription-based model, right? You can subscribe to multi-cloud in real time. You come to business system, you make your request, you specify your business requirements, bandwidth, latency, what VNF you want, what cloud you really want, and we already have cloud integration. So our BSS system already talked to big cloud providers. We have API integration, so we can log into your VPCs or with the service keys that you provide us. We can connect these direct connect circuits and then stitch it to the VNF. Easy to develop new services. When we bring up a new VNF, it should be easy to deploy. We don't want to spend like months and months to just repeat the same process for Arista VNF or Fortinet VNF and all, right? It should be easy to develop. Customer beyond Equinix Colo. So currently, With the Cloud Exchange physical fabric, you have to be on Equinix data center to consume the multi-cloud goodness through our E6 fabric. But this product says you don't need to be on Equinix premise. It's a virtual point of presence, and your virtual point of presence could be a routing VNF, firewall VNF, or SD-WAN VNF, or load balancer, whatever you like. So product requirements are simple. Standard HC-based architecture, right? That's pretty standard. Performance should be 1 gig, 5 gig, 10 gig, and 40 gig. We are not talking about like 10 meg or 20 megs here. Monitoring, proactive monitoring of the infrastructure. All OpenStack storage, controllers, Keystone services, SAF services, Nova services. This is one piece, but peer network. You have network beyond OpenStack networking gear, right? The peer network. Everything should be monitored, and you should be able to correlate when the event happens. So let's say you are hosting a VNF on a compute goes down. You need to know how many customers got impacted, and then you place the VNF to available compute nodes. So very robust monitoring system needed. Capacity management and scalability is a big challenge that currently we don't have on an OpenStack. I'm real-time placing the VNF. I don't know when it goes out of resource. There is an API you can call, but then you need to build all the intelligence somewhere. That's what pretty much is lacking currently on the OpenStack. High available and resilient services. So you build highly resilient service, meaning you should offer a cluster with HA feature. You should have plane A, plane B's, primary and secondary within a cluster, availability zone, and the scale that Equinix has, customer are asking, I want cluster redundancy, I need metro redundancy, I need regional redundancy. So the variation of redundancies that you need to provide to your customers. Then resource availability management, placement logic. So if I get 2 requests from a customer and I'm trying to place it right at the top layer of BSS, I should know on which cluster I should have resource available so I can place it. I don't want to go down to the cluster and try to place the VNF and it fails, then I come back and try the next cluster. So right at the top layer, I need to know which cluster is satisfying the incoming customer requirement. So if we recap HC architecture, it has VIM, which takes care of your NFVI infrastructure build out, right? So there's a VIM component. Then they have VNFM, which is Virtual Network Function Manager. And third component as NFV. This is an orchestrator. When your NFV comes up, how you push day one configuration to build services. So now, if we map it to Equinix stack, we have Cisco VIM. What it does, it brings up the complete stack with single YAML file. You put your request in a YAML file. You already know your network component, the IP addresses, DHCP, naming convention, cable run list. You fed it into your YAML file, submit it, and it brings up your complete stack up to the aggregation layer. So again, we talked about it in last presentation. There are 2 types of model. One is micropod, which is smaller version of the stack. One is complete pod. So VIM takes care of provisioning your compute stack plus the top of the rack connectivity of these compute stack. Pretty handy. Now, the next layer is VNFM, which is ESC, which maps to Virtual Network Function Manager. It takes care of your day 0 configuration. When VNF gets spawned, then you push day 0 configuration, which involves your TechX configuration, your management stack configuration, how you get connected to management stack, a DHCP, and all that stuff that ESC takes care of, and also a placement logic. ESC has a placement logic. When VNF comes up, it keeps pinging the VNF with specific cadence, which is configurable. When it fails to ping for the defined cadence, it tries to place the VNF automatically to available computes. If it fails, it relays the message to the upper layer, and then we have another second layer of logic, how to place it. So all the goodness is built into different layer that we can abstract it to higher layer and make more intelligent logics there. Then you have NFV-O, which is an NSO layer that we have. This NSO layer, we have 2 layers of NSO. As I talked about, we have ECX fabric. It's all automated, fully automated ECX fabric. So we have NSO already deployed, which is, we are calling it PNF NSO. We decided to go VNF NSO, so we can have 2 layers totally segregated. So there are 2 NSOs currently deployed. One takes care of the physical network function, other take care of the virtual network function. If I talk about PNF, this NSO will provision ECX fabric and all the direct connect circuits from the cloud up there. So let's say customer comes from Equinix Orchestrator. He says, I want to connect my private cloud from Microsoft, on Amazon, and Oracle with 1 gig of bandwidth. Request gets dispatched. Some request goes to PNF NSO, some goes to VNF NSO, because you need to stitch the VNF to these private clouds. So it goes to ESC. You spawn a day 0 configuration, because day 1 configuration from NSO. You build all the plumbing of the VNF to the NIC card, and you connect it to the private direct connects to the ESC. I oversimplified it, but the idea here is VNF and direct connect circuits get stitched together. You do VNIs, VXLAN, I talk about in my next slide how we're stitching it, but the functionality is all microservice, and every specific component have their own functionality to deliver to stitch the circuit end to end. So you do BGP, and then magic starts where these clouds talk through VNF here. Network forwarding, scalability, resiliency requirements. So now our ECX fabric here, the requirements are simple in this. You have to support 1 gig, 10 gig, 40 gig VNF throughput. That's one of the key requirements. So what we had is, this is my compute cluster. We implemented VPP, Vector Packet Processor. We evaluate OVS DP-DK switches, and they're flow-based. When you increase the number of flows, performance degrades. They match on 5 tuples. And when we try to scale number of flows to 4,000, 5,000, 10,000, performance degrades. We start looking for alternate option and figure out VPP is the best option, and VPP does the forwarding lookup based on the MAC and an IP table. So think of it, you're bringing a physical router microcode, you're bringing it into as a kernel loadable module in a Linux kernel. And that's the power. So you have VPP, VPP give you 40 gig throughput right now, and we are doing trials with Cisco, it can go to 80 gig as well on IMAX packet sizes. It gives you all the tap point. If you see here, when it create a VNF and stitch it to the NIC card, you create Linux bridge in a VPP. Now you have a tap point, and traffic when it starts from VNF goes out. From VNF to VPP, I need the number of packets flowing, and from Linux bridge to NIC. So I need all that visibility. When my ops get the call from the customer, they need to know, they need to have a visibility how much traffic is going through each component or forwarding component within the compute stack. On-demand traffic mirroring capability. We build the capability where we can tap the traffic coming from any of the VNF on demand. If customer calls in and says, this is my VNF, I'm seeing packet loss, or traffic is not flowing, we have a capability we can tap the traffic on demand and look into the packet details. So this infrastructure is get connected to top of the rack, which gets connected to Cloud Exchange Fabric, and then you have a path to the cloud provider. Now, support of tunneling mechanism. So once we solve this packet forwarding problem, the next problem we start getting is I can host close to 1,000 customers, tenants on this platform. When I say 1,000 tenants is, we have physical carving of the resources. If I say 1 gig VNF, I want to host this platform, every 1 gig VNF takes 2 cores. So now, this is our benchmark to say this cluster, if they have 2,000 cores, total cluster, I can host 1,000 1 gig VNFs. That's how we are benchmarking the platform. Now, every VNF can have 10 to 20 interfaces. Every interface is a VLAN. So what we start seeing is we are running out of the VLAN capacity. We start figuring out that we need some tunneling mechanism right from VPP up to my Cloud Exchange Fabric. So there are 2 options that we had. We can go either with VXLAN, or we can go with segment routing or MPLS. So currently we pick VXLAN, but eventually when my fabric convert into from LDP to segment routing, I'm going to move this VXLAN tunnel to a segment routing. I'm going to I want to start pushing the label right from the VNF up to my Cloud Exchange. So now, to solve this VLAN challenge scalability problem, we are doing VXLAN tunneling. Every compute has one VXLAN tunnel going to my Cloud Exchange fabric, all the VNF on this compute, get the VNI, traverse the VXLAN tunnel, terminate into my ECX fabric, and then get stitched to the cloud. So now, to do the cloud stitching, I create a direct connect. Direct connect is nothing but a VLAN extension from the cloud, terminate them in a routing instance. So I start learning the MAC addresses from the cloud. Okay, so MAC A on the cloud, private cloud, comes and get learned in routing instance on MAC A, here on the purple circle. It get learned to the customer routing instance. Now, the challenge we start seeing is how do I make sure this MAC address get learned to the VNF? There are two ways. I can do flattened learning, then I lose my bandwidth, or I use goodness of EVPN, so I can learn through EVPN to my VNF. Now, two implementation that we had, either we bring the control plane all the way to the VPP, or have a centralized controller and distributed line card architecture to learn the MAC and then program it on my VPP. So we come up with scalable architecture where you have a centralized controller sitting and agents sitting on all of the computes, which is nothing but a forwarding plane, have a route reflector. Sorry, all of these agents talk to this controller through a REST API, have a route reflector talking to my ECX fabric and this central controller. So that the MAC now be learned through route reflector, it goes to my controller, goes to my database here, and get learned here. So we solve this control plane scalability problem with GoBGP and VPP agents sitting there. If you, from 10,000 foot, it looked like you have a centralized control plane and distributed data plane. It's very scalable architecture. We have seen the scale out of 128 compute clusters, 128 line card, and one central processor. So it's pretty scalable. We can do thousands of VXLAN tunnels per compute. So now if MACP get alive on the VNF, it get learned to this data store, go to BGP, control plane, get learned here, go to the cloud. Then you run BGP, and then you send the traffic. No flattened learning in this network. Second problem that we faced is service chaining. So we have a routing, and then we have a firewall, then we have a load balancer. We were proposed SRIOV solution by various vendors, but the problem with SRIOV, it's talked directly to the NIC, and when you do service chaining, the traffic goes to the top of the rack and come back. So you lose lots of bandwidth between your compute and the top of the rack. So how we achieve network optimized service chaining is, this is again one of the compute. If this two VNF needs to talk to each other, you create a Linux bridge on the VPP, you stitch them together, and then traffic doesn't even leave. If you're two VNFs on the same compute, traffic will not even leave your compute, go to the top of the rack. We will do local forwarding and chain it and then send it to the cloud. So that's one of the goodness that we achieve with this architecture. Now, high availability. So OpenStack itself provide aggregate host concept. We consume aggregate host concept and provided 4 types of high availability to our customers. So requirements were NES should leverage platform Equinix global footprint to provide HA for cluster. So this is one cluster, meaning if it's a micropod, then 60-node cluster. If it's full pod, it's 120-node cluster. So we created plane A and plane B from these clusters. So let's say 128-node cluster, 64 nodes are plane A, 64 nodes are plane B. The abstraction at OpenStack layer is aggregate host. So you have 2 aggregate hosts you created, and customer when comes and asks HA, cluster level HA, which is cheaper, we will place VNF, primary VNF on plane A, secondary VNF on plane B. Second is data center level HA. So you have a region, you have a metro. Within the metro, you have 2 data centers. You place 2 clusters. Again, if you double click the cluster, there'll be plane A in a cluster and plane B. So if customer comes and asks us HA for a data center, we place primary VNF in plane A in DC1 and secondary in plane B, DC2. Then there's a metro HA. So same hierarchy, you have a region, you have two metros, DC metros, and Chicago Metro, and then you have two data centers, could be one or two, and then every data center has plane A, plane B. So here the key is customer want metro diversity. You make sure you pick two different metro, and one metro will place plane A, other will be plane B. Then regional level. So same footprint here. You have region, two regions, and then within the region you can pick any metro in plane A and any metro plane B. So it's a regional level HA. You have plane A in metro 1 and plane B in metro B. So it's a customer choice, whatever way he wants the HA to be built out. But we consumed here OpenStack level of aggregate host functionality. But what's missing in OpenStack here that we're building ourselves is capacity management here. How do I know how much resources are available in which cluster? Because when you place in plane A, plane B, you need to know ahead in time at the BSS layer that which metro and which cluster has capacity available. There's an API available, but then you need to consume the API, build your own logic, which becomes really complicated when you do real-time provisioning. So with this architecture, customer can build very scalable overlay networks on top of this infrastructure. So now let's park and let's talk about the failure scenario. So if customer has to build robust overlays and there's a failure happens on your cluster, what happened? Here what I'm showing is customer has a primary VNF on plane A, secondary VNF on plane B. And if you see the cloud, the way the connectivity happened with the cloud is customer also have a primary cloud instance and the secondary cloud instance. So the way we orchestrate it is your primary VNF will connect to your primary instance of the cloud. Secondary instance will connect to a secondary instance in the cloud. So if the plane failure happens, your VNF in plane A goes away, but you still have a connectivity for the second instance in the cloud. Network failures. If your ECX fabric fails, customer will still have a secondary VNF goes to the cloud. So that was all about the resiliency, and it covers data center failures and metro failures as well. The third challenge that we had on top of OpenStack is to build a robust monitoring orchestrator. So if you've seen, the requirements are you have to have proactive monitoring of OpenStack resources. When I say OpenStack resources, you have OpenStack services, Nova, Neutron, Keystone, all of these services. Then you have storage component there. Then you have a controller component there. Then you have a VNF sitting there. Then you have a hypervisor sitting there. Then we have VPP. Then you have a VNIC, then NIC, and all that stuff, right? So that's proactive monitoring. We don't want a pulling mechanism. We want push mechanism. Things happen. I want to catch that event and act upon it, right? So that's one of the requirements. Second requirement is proactive monitoring of hypervisor level resources. Third requirement is proactive monitoring of VM and VNF level resources, all the VMs and then VNF. Then fourth requirement is proactive monitoring of traffic in and out of VNet, VPP, and the NIC cards, and capacity management. And then build an automation, API-driven, event-driven, and do all the correlation of all the events. One of the challenges that my NetOps gives to me is when I get a call from a customer, he tells me the specific VNF is not working. I log into the dashboard and I should have some knowledge beforehand. So you need to start correlating the event. When you have to correlate the event, you need so much of knowledge from the network. And as much knowledge you have, the better decision you can make or correlate. So you consume all of these. So first of all, Ceilometer is pretty restricted to what it can give. It's mostly focused on Neutron and all. It gives you some storage component as well, but complete stack knowledge is not there. So you got to build something else. You pull new Ceilometer, then you pull some raw APIs, and try to correlate yourself as well. So now, once you get that information, Equinix data center, if you see, is more hierarchical. You have 3 regions, and every region has metros. And in the metro, you have multiple data centers. So once you get that information, you need to start correlating across different data centers, metro, regions, because you don't know, customer have chosen a metro level HA or regional level HA or DC level HA. So you need to start doing complex correlation, which is the main brain and recipe here. Calling an API is an easy thing, but then how frequently you're pulling the API, if it's a pulling mechanism, it's a push mechanism, all that stuff. The latency to know the event is really important for you to make the real-time call. So we build all that in this infrastructure. Now, I'll talk about 3 big use cases. The first one, we talk about multi-cloud routing. So using this infrastructure, first service that we're offering is called virtual multi-cloud routing as a service. Meaning, as we talked previously, current way of operation is customer connects their private cloud over the internet. They run IPsec, problem with latency, problem with bandwidth. With Equinix, if you build this infrastructure, customer can connect through a private ECX fabric with a virtual point of presence, which is a VNF here, and then traffic route will be through a private cloud, secure, private. You can get up to 40 gig bandwidth on your circuits, because main problem is not the cloud, is not the ECX fabric. Main problem is a VNF. You cannot get high throughput on this VNF. And if you try to go with SRI or you pass through mode, then if the failure happens to the VNF, moving the VNF to a different compute becomes very challenging. So we need to abstract this. So the VPP is give you Vert IO layer with the VNF, and it gives you DPDK with the NIC cards. So you don't have hard pinning off your VNF to the NIC cards or VNIC. The second use case we're trying to solve it, virtual private network as a service. As you already know that SD-WAN is picking up, but so many customers already have vanilla routers sitting on their branch offices. And if you want to consume a goodness of the cloud, what we can give an offer is customer can VPN to a VNF. So if you can invoke a router VNF here, you can enable an IPsec. Customer can bring their branch office securely and can go to the cloud natively. Don't need IPsec encryption there. So VPN as a service is use case 2. Use case 3 is DMZ as a service. So currently, the way the three-tier architecture is deployed in enterprise network is you have a web tier, you run load balancer firewall tier, then you run application tier, you run firewall and load balancer, and then you run a database tier. This is how a typical 3-tier enterprise application is built. Let's play this scenario to the cloud. When you go to the cloud, you can have your application, a web tier on Amazon, application tier on Microsoft, database tier on Oracle. Then you implement 3 firewalls for all these clouds. With this use case, if you enable this use case, you can still have your application and web tier at Amazon, application tier on Microsoft, database tier on Oracle. Since traffic is traversing across the VNF, you can normalize these 3 functions to one place, and then traffic will traverse through Equinix, and you have to normalize these functions to a VNF here at Equinix. So you save money, you save operational expenses, all that stuff, and it's simple to deploy. Fourth use case is SD-WAN as a service. So what are the challenges we are trying to tackle here? The way traditional branch offices access the cloud or internet is they have 2 circuits that goes to the internet or the cloud. One is through internet, and second one a backup or primary is through MPLS. But they have a central data center sitting somewhere. All of their branch office traffic is backhauled to their central data center, and then it's routed back to the SaaS or to the internet because they wanted to centralize the firewall operations right at the central office, right? That's one scenario. This is operationally less expensive because it's only a head office that connects to the internet. Everything is private here. So you really don't go through internet. You backhaul through MPLS to your central office and go to the internet. Easy to operate, but it's very expensive for the branch office who's sitting in the West Coast. East Coast will see good quality because your central office on the East Coast, but West Coast see high latency because he is backhauling all the traffic through MPLS network to your central office, which resides on your East Coast. So Not very viable option. Use case number 2, if you want to have branch offices access the cloud destination directly from the internet, you have to implement a VPN and firewall. So if you have more branch offices, you need operationally the network, manage this network is very expensive. You need to make sure all policies are compliant, nobody is touching it. You need an operation guy for every branch office, or some guys, some team that they will look after your managing the firewall at the branch office because you're open to the internet. So now, how Equinix will solve this problem with this platform is, if you have a branch on West Coast and the East Coast, Equinix Colo exists on the West Coast. You have a SaaS destination reachable through Cloud Exchange platform. If you deploy SD-WAN headend for this company on the West Coast, same thing you do on the East Coast, and install your branch SD-WAN routers, and based on your BSS application, you can tell customer what is the quickest and low latency path to go to the SaaS and route their traffic accordingly. So that's the play here is, every branch, you know the location of the branch office, you know Equinix locations, and you can create a good latency map for the specific customer, and on demand, install these SD-WAN through single click, and then push policies so we can route the traffic to the better path. So the key takeaway for the OpenStack forum is lack of supporting robust data plane currently on OpenStack. 1 gig is easily achievable. We try to do OVS DPDK, 1 gig with OVS DPDK. We have to use 6 cores compared to when we start using VPP, we are using 2 cores for 1 gig VNF. So we are saving a lot on forwarding side. Lack of supporting robust routing solution to interact with layer 2 and layer 3 subsystem. Building VNF orchestration is good. Yeah, I can spin up my VNF, create, delete, remove, but now I need to connect this infrastructure to the peer network, which is fully routing heavy. How do I bring that routing goodness to the OpenStack? It's currently lacking the routing robustness. There's no SD solution there. Third one is lack of support of robust monitoring infrastructure to give me complete visibility of my OpenStack software and hardware stack. Upgrades are nightmares. So that's why we come up with the HA. We have availability zones, and customer have primary and secondary, unless we start seeing some goodness on OpenStack. We're working with Cisco really to make it a millisecond when you have upgrades, millisecond downtimes. So HA will not be that suitable. So we need product, not pieces. Currently, you can take it, you can do bits and pieces, but building an entire product, it's just not there. So I'll hand it over to Google to take us through the journey of how they implemented it.
So in the interest of time, the use cases were very extensive, and it took quite some time to explain, because it has to reach out to the audience properly. So as the use cases were sophisticated, we already ran out of time. So I don't want to overlap with other sessions moving forward. So what I'll do is I'll quickly cover this in a minute so that I can hand over to the other session. So one of the major shortcomings, like what MD was explaining, was a robust monitoring system, lack of robust monitoring system. So prominent co-located data center players such as Equinix requires a multi-region and multi-metro monitoring infrastructure where they can monitor the whole infrastructure in a single pane of glass. So with Prometheus today being one of the biggest community-oriented monitoring scheme, and also Grafana for visualization, Prometheus as is has multiple bottlenecks in the implementation. We cannot replicate TSDB without another layer like MariaDB, or if you have Kubernetes platforms and all these container platforms, you need something like a persistent volume provisioner to replicate the TSDB data. So what we have come up is a sophisticated monitoring stack, which can drill down from the top of the tree, which has a region, to metro. And metro might have multiple OpenStack clusters, and region can hold multiple metros. And OpenStack cluster, you have the visibility to the project, tenant, compute hypervisor, then finally your VM. So much granular, more sophisticated monitoring system that we term as CVIM-MON, which is CVIM Monitor, like which monitors the multi-metro and multi-site deployments of Equinix that they have them geographically distributed around the world, or they can do a monitoring based on the labeled-based monitoring stuff. So this is the architecture overview. We are leveraging Kubernetes to make Prometheus and Grafana high available. So we are leveraging a totally different platform to enable like Prometheus to get its high available nature. So there is a very strong reasoning behind why we chose Kubernetes in this context, because we are only running one replica per metro or per region. So we are only running one replica of Prometheus, because we cannot run Prometheus in active mode. As many of you might know, there are many services in OpenStack like RabbitMQ and other stuff, which are very sensitive and which are very susceptible for the like footprint metrics and other stuff. So for example, if you run Prometheus in active mode, the three Prometheus appliances will reach out to the cluster in different scrape intervals. So we can only run one replica of Prometheus, and we had to make that HA. So Kubernetes came into the rescue, and Kubernetes is the basic platform, and primitives of Kubernetes helped us to make Prometheus highly available. So we use Kubernetes native scheduling to schedule the Prometheus instance to another node when the node fails. So this is totally making Prometheus highly available using Kubernetes primitive or Kubernetes native scheduling. So we at Cisco believe Kubernetes and OpenStack are two complementary technologies which can complement each other and even make a big difference if like we use them together. With our other initiatives such as CCP with CVIM, which is Cisco Container Platform with CVIM and all other initiatives, we are already proving that like these two complement each other and not rival between each other. So so this is how like we enable the high availability using Kubernetes platform, and ending with the way that it interacts with the Kubernetes cluster here. So we don't usually follow the same open source construct of using Telegraph. We have an intelligent proxy which will be listening on all your controllers over a web, and that proxy collects all the metrics from all your cluster. So this put light on an important aspect where this brings down the scrape configuration that we have to provide for Prometheus to one line, rather than providing 10 to 15 hosts in the cluster. So this is only one endpoint where the intelligent proxy knows how to collect metrics when Prometheus reaches or hits this particular endpoint. So this is how we are managing the namespace multi-tenancy. So for it is on-based, like on-demand monitoring stack provisioner. So the total orchestration is a single-touch automation where the users can deploy multiple stacks of monitoring solutions on top of a single Kubernetes cluster running in HA mode using the namespace segregation, and they can name their namespace using the metro name. So whenever a node fails, the total stack will be redeployed on the other node using the replica set and deployment of Kubernetes constructs. So like I can go through in much detail, and you can always reach out to us in one of the booths like that we have in the marketplace, so we can talk about it furthermore. And sorry for the inconvenience, as we had so much of stuff, we could have made it simpler, but it needs more time to explain the sophisticated use cases. Thank you.
Thank you both. Just in the interest of time, if there are questions, and I'm sure there probably are, we're going to have to take that into the hallway track. We have to make room for our next session. Hope you'll stay and join us. Miguel, if you want to come on up, we're going to try to keep this moving. Actually, though.